Good morning. Is that right? Yeah. Got me? Okay, good morning. It's so great to see everybody here. This is like becoming my favorite week of the year. This is our third, right? It's our third Mineral X. I want to do a quick poll. Raise your hand if you're here with a company that is a part of the Mineral X consortia. Okay, very good. Now, raise your hand if you're with a company that's not yet part of the Mineral X consortium. Okay, great. Welcome. You are very, very welcome. And I speak from experience that the ROI for being a part of the Mineral X consortia is phenomenal. It's fantastic. So if you're not yet a part of the consortia, I strongly encourage you to consider joining. Talk to Jeff. The benefits are highly nonlinear. The cost is not very much, and you're immediately connected with the scholars doing some of the most cutting-edge and exciting research related to critical metals and applying advanced scientific computing, AI, et cetera, to the discovery, mining, and development of those. It's really, really, really cool. And as a member of the consortia, you will get to craft the research. Like it is very much a two-way street. We're inventing and evolving Mineral X all the time. So the wrong way to think about it would be like, oh, I'm not interested in that, I'm interested in that, and that's the wrong way to think about it. Think about it as what really hard questions do you have, do your businesses face, and questions you want to bring and collaborate with some of the most brilliant scholars in the world on, and the other member companies. Okay, that's my pitch for the day. The objective of my talk I've got is to convince as many of you as possible of four things. And here they are in decreasing order of importance. Thing one, all geoscience data currently possessed by governments that was collected at the public's expense should be made public immediately. Thing two, all geoscience data possessed by governments that was paid for by private companies should be made public extremely soon. Thing three, all data that will be collected by private companies through mineral exploration, development, and mining, the companies that collect that data should be working under the framework that the data will be turned over to the right authority, or a copy will be made to the right authority at the right time, and that data will become made public. And then thing four is actually the weakest of my claims, the claim that I hold the least strongly, and that is that governments should fund, to some degree, widespread geoscience data collection. Okay? 4 objectives. Let's see how I do. Let's go back in time to when the Industrial Revolution is heating up. People wanted to move coal from mines to mills and factories, and so they started building canals. First all over England, and then all over the world. Of course, once the canals were built, they moved all kinds of things other than coal, all kinds of goods and people, which accelerated local and global trade. There was another really cool benefit to digging these canals. These canals are effectively long trenches cut through the side of a country over hundreds of kilometers, exposing the bedrock material. Right? So many canal engineers and just normal laborers started to notice that the strata that they were exposing over extremely long distances repeated themselves. It was oriented in predictable ways, and they could actually predict what the strata would be before they dug it next, based on what they were observing. One individual, a fellow named William Smith, took the idea a step further, realized that we had this large canal network throughout England and Wales. He combined the new observations made by those rock exposures with observations of rock outcrops around the country, and then interpolated between the long canal cuts and the outcrops to predict the composition, the form of the bedrock throughout the entire country, all of England and all of Wales. The actual exposed rock face was significantly less than 1% that he based all this all these predictions on. He drew what is widely regarded as the first ever geologic map. This basically spawned the start of what we currently think of as modern field geoscience. So people, I have to click that start. Yeah, people spread around the world doing similar mapping exercises, mapping basically the entire continents. And now you can hop on the USGS website. It's a nifty tool. The USGS has stitched together thousands of maps that were collected over many, 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 many decades, right, by different authors. You can click on any of these maps. You can download the base map. You can see what the original data source was. This is incredible public access to geoscience information. You can go to anywhere in the continental United States and immediately develop context about the local geology. Super interesting. Unfortunately, it is the exception. In our estimation, well over 90% of information that humans have collected about the physics and the chemistry of the Earth's crust remains like this, right? Either in paper form, large, think stacks and stacks of compendium reports, drawers of geologic maps, and core, right, in large warehouses. Huge amounts of information. Think about the information content in a rock core that was extracted from a kilometer deep below the ground, the location and orientation of the core, the rock types, the composition of the material, all that kind of stuff. Huge amount of information content, incredibly difficult to access and use. So humans have spent all this effort collecting all this information about the Earth's crust, and it's very, very, very difficult to use and not available. We spend at KoBold, well, many of us spend like all day, every day, thinking about where we want to explore, and where we want to invest our capital, where data is been collected, right? Where data, where there is an endowment of data, and where that data is easily available. So this is our judgment of basically where data has been collected. And as unsurprisingly, it kind of tracks industrial development. Green is lots and lots of geoscience data collected and so on. And it also tracks a region's mining legacy. But it doesn't necessarily correlate with how available the endowment of data is. So here's our judgment on that. Okay, this is how easy it is to get the data. Go back and forth. I suspect nobody in the room is surprised to learn that Russians have collected lots and lots of data about Russian geoscience, but that data is extremely difficult to get. They drilled the deepest borehole in the world, over 12 kilometers. It's basically impossible to get any meaningful geoscience data out of Russia. Not surprising. Maybe more surprising is a fair number of countries, particularly developing countries, who are actively trying to seek foreign direct investment into their natural resource sector, and they have not made the whatever data endowment they have easy to access. Part of this is just state capacity. It's hard. It requires sustained budgets, sustained groups of technocrats to build a library service, to maintain digital archives, all that kind of thing. You'll notice even the United States, we don't give a green score to on data availability, despite that cool USGS tool that I showed you, because the USGS, still 90% of its records are not even digitized. But there's another reason why countries don't make their data easily available. I was really, really happy when the Ukrainian minister, I think has left, unfortunately, but when he said, it's stupid that we classify this data. That was fantastic. He reiterated that to me in the hall. And he's totally right. So I look forward to switching Ukraine on this map from red to green when they follow through with their, with their commitments. But the other reason why countries restrict access to the data, besides understandable reasons of just it's difficult to do, to make available, is a misconception. A misconception about the reality of what the data is, and which leads to very poor economic reasoning. And this is the idea that the data represents a treasure map, that the data is itself a treasure map. Because you can imagine if the data were a treasure map, right? If the data set that you had actually just told you where all the economic deposits were and had beautiful characterization of all of them, well, sure, I mean, maybe that would be a national security secret. Maybe you, in that case, you just actually wanted to auction off the deposits probably. It's a different thing, right? But if the data is in fact not a treasure map. I am sure lots of people in the room right now are thinking, he's making a straw man argument. He's making that up. No one thinks the data is a treasure map. But I'm not making a straw man argument because politicians all over the world act as if it's a treasure map. They act as if it's a treasure map all the time. And that's bad, and it limits investment in the industry. It is not a treasure map. I want to prove to you that it is not a treasure map. So these videos are annoying me. Let's see, there we go, good. So be patient with me for a second, because I want to hit this really hard. So here's collecting data. Okay, this is 2 KoBold efforts. The thing on the left is the KoBold Hyperpod. This is probing the surface of the Earth with LiDAR and with a set of cameras that are taking super high resolution pictures in 600 colors beyond the visual spectra. And then the thing on the right is a geophysical survey. It's being guided partly by KoBold software. It's probing the depth of the Earth's, gathering information about the distribution of the conductivity, the magnetic properties, and the density of the rocks below ground. Just the Hyperpod collects almost a terabyte of data every hour that we're flying, okay? So that's how we collect some of the data. There's something like 100 different data types. I'm only going to talk about 2 with respect to the treasure map idea. So here is, let's see. Yeah, there we go, good. Okay, so here is a partial excerpt of a data set from a very small electromagnetic survey. When I say small, I think about 10 square kilometers, okay? We would have to sit here for 20 hours watching this scroll to see all the data, and we would only see a third of the data there because I'm only showing you 50 columns. It's actually 150 columns across, okay? I'm actually going to tell you what this data is because it's really, really important. So we're going to go from left to right. The way an electromagnetic survey works, you saw that loop, right? This is actually quite analogous to a metal detector that you'd see on a beach. It sends out an electromagnetic pulse into the air. That pulse goes into the ground. It generates eddy currents in all the materials underneath you. If those materials are conductive, those eddy currents are long-lasting. If they're resistive, they decay quickly. In any case, they decay, and when they decay, that itself induces its own electromagnetic field. We can listen, quote unquote, for that EM echo effectively at the source. Each one of these rows is one EM pulse, okay? One EM pulse. That's the first column, just the pulse number. There's 1 million pulses in this small survey, so we have 1 million rows, okay? Order 1 million. The second column is the date at which the survey was collected. Third column it's called diurnal. That is the background magnetic field. You have to subtract off the Earth's magnetic field in that area as a part of this survey so that you get only the active component, which is not measured actually on the aircraft. It's measured at a ground base station elsewhere, and it takes a lot of judgment to adjust that. The next 2 are just longitude and latitude of the location of the sounding, which is changing constantly because you're flying. Okay, now you get into the physics data. Magnetic fields are vector fields. They have 3 components, right? So we are measuring the magnetic field in the vertical direction, the z direction, as well as in the x and the y direction. And we're measuring how that magnetic field is decaying because the eddy currents underground are decaying. So the first number, you see 2.9 up there underneath the EMXBF final. That is the first measurement. I'm only showing the x component of the B field here. That's one component. And that's measured in picotesla. Okay, so it's 2.9 picotesla. That's measured about 50 microseconds after the pulse. And And then the next one over is just the next measurement. This is based on the sampling frequency of the receiver, which is about 0.05 microseconds. So we collect this for 25,000 microseconds. That's each pulse. That's why there's 150 rows to the column. So you have to go through all the x components, then all the y components, then all the z components. We also measure the time derivative directly of the B field. Okay, so that's the raw EM data. That's it. So where do you want to dig? Where do you want to dig? Now, I'm sure you think, oh, I'm sure there's just a standard geophysical technique that takes all that and tells you, drives something useful from it, right? Okay, so sure, there's lots of, geophysicists do lots of little tricks with the data. I'm just going to take you through a couple of them. So here's one. This is we just plotted on a map and then interpolated between the data points. We plotted the first received measurement of the vertical component of the magnetic field alone. So only the first measurement, it's a time series, and only the vertical component. So that means that's less than 1% of the data. Less than 1% of the data. I've thrown away 99% of the data. But geophysicists love to plot these, and geologists love to look at them and think about what's going on there. Okay, so what do you think is important? But maybe we should look at the last measurement in that time series. Okay? Which one's more important? Well, they're both important. But they certainly, neither one tells you where to dig. But it's a decay, right? So maybe we should be thinking about the rate of decay of the curve, okay? So here's one way that there's lots and lots. You have data points. You got to fit a curve to the data points. Usually the curves decline monotonically. Not always, actually. Sometimes they have an inflection point. So you want to fit a curve to it. And here a common technique, which actually sort of baffles me, is that you fit, along the decay curve, you fit 5 segments, 5 different exponential decays to the curve. So you have 5 equations, 10 parameters. And then you pick the smallest decay parameter, and then that's what's plotted here. Okay? And then this is just another way of actually measuring the rate of decay. Doesn't matter, I won't explain how, but it's another way of measuring the same thing. There's endless possibilities. Okay? And the point isn't to dunk on any of these techniques. This is just people exploring the data. We do it all the time. Shout out to Beth and Lauren will be talking tomorrow about some of KoBold's techniques to look at this data. But the point is, it is far from a treasure map. Let's go back to the geologic maps, right? The first ever, you remember the William Smith map. This is a much more modern map. Geologic maps are really interesting things because they're showing, they're asserting the superficial or bedrock composition of rocks over large areas based on a sort of scarce number of observations, right? And geologists will name the rocks. And that name actually incorporates 3 orthogonal pieces of information. Something about the composition of the material, right? Is it a mafic material? Is it a felsic material? Something about how that particular body was formed independent of its composition, as well as the relative age of that material relative to its proximate rocks. It all gets embedded into one name. So in this map, you have the lower BR and the upper BR. They're just different names for that area. This is mapping in Ontario. The map stops halfway through because they ran into Quebec, and this was funded by the Ontario Geologic Survey. So the Quebec Geologic Survey picked it up on the other side, and they used a different set of standards, different set of rock names. They had 9 rock categories. And it's not like, I'm not trying to even dunk on the authors here, because this is really, really hard to do, and there's a lot of subjectivity. And if you heard the authors describe each one, you would be compelled in a way by the way they classified the rocks differently. It would make sense. They're also making very, very different predictions, right? In some cases, they're saying you're going to walk across the ground and the rock is going to be the same for 20 kilometers. In another case, no, you're going to cross over 7 different rock bodies over that same period, right? So even the simple superficial map is by no means a direct detection method. People know, and I think we'll talk a lot more about this over the next day or so, that exploration is getting a lot more expensive over the last 4-5 decades. the measurement we like to track is number of discoveries per $1 billion of cumulative exploration expenditures by the whole industry, okay? So a generation ago, that was about almost 10, and now that's less than 1. Right? We call this E-Room's law of mining, which is Moore's law backwards, right? We're getting less good at it over time, but this isn't actually so much of a criticism as it is just a statement that the search space is getting way, way harder, right? All the sort of inventory of directly detectable things at the surface, the things that a geologist could walk up and identify ore minerals in the outcrop, that inventory has been culled. And so search space is much harder. It is much more, exploration is more expensive. Success is less common. To find the materials of the future, we need to attract risk capital. And how do you attract risk capital? Well, there's lots of ways. You just heard a panel of people thinking about clever ways of public finance. One simple way, one free way, is to provide the data that's already available to all the companies willing to take those risks. And this isn't hypothetical. There's some cool examples of this working well. So in Bolivia, eastern Bolivia in the 70s, there was no exploration activity, no mining. And the British, Swedish, and Bolivian geologic missions collaborated on a fairly extensive studies over a wide area, did geochemical sampling, geologic mapping, and geophysical survey collection, and then they just published the data. Within a couple years, they went from 0 to 35 companies exploring and investing in the area. And within less than a decade, you had 3 operating mines in that area. Of course, that's just an anecdote. Let's look at another slightly more quantitative version that's been, geologic surveys love to talk about this example. This is the Bay James region in Quebec. And in the 90s, the Quebec Geologic Survey funded a set of geochemical surveys, extensive geochemical survey throughout this region. You can see the dark bars are public funding and the private bars are exploration investment during that time by private companies. The data was published in 2001, and then private sector exploration investment skyrocketed. Really cool. Of course, there's some confounding variables. Well, let's see. One says, so the investment was something like 25x. If you just look at the cumulative amount of private investment relative to the cost of the public survey. Does that mean that every government that funds this kind of stuff will get a 25x a return on investment in terms of inducing exploration activity? No, for sure not, because of the confounding variables. So one confounding variable is there was a big discovery in Bay James shortly after the publication of the data. It is consensus view that the discovery was helped a lot by the public data, but then the discovery itself led to a sort of private land rush and lots of investment. And that's kind of the virtuous cycle that you're looking for, but how much of it is attributed to either one is a little hard to say. Of course, there's another gigantic confounding variable, which is that commodity prices skyrocketed during the time. And so that's very difficult to correct for. But maybe one way to look at it is just the share of exploration activity by dollars taking place in Quebec, or taking place in the Bay James region of Quebec versus everywhere else before and after the publication of the survey. And that more than tripled. So that tells you something about this. So scholars have tried to quantify that multiple better, that return on sort of induced exploration expenditures. This was first done in '99 by a guy named Bolton, and then people have tried to repeat it. And they subsequently tried to quantify the uncertainty of the estimates. These are sort of all over the map, right? Because it's really hard social science to do, actually. You've got a lot of confounding variables, and how you attribute the results are really difficult. So we don't put a lot of weight into this, and that's why I say, whether the taxpayers should pay for new exploration data is I don't know, it's a tough call. Taxpayer money can be used for a lot of good things, right? So let's break this down now, data as paid for by taxpayers and not paid for by taxpayers data, and in the public domain versus not in the public domain. Okay, I've got 4 categories of data. Okay, so if it's paid for by taxpayers, it should be in the public domain, right? Obviously. Anyone disagree with that? Okay. How about if it's not paid for by taxpayers and it's in the public domain? We think this is great. We're a private company. We think this is great. Why is it great? It's great because the jurisdictions that do this under a very clear set of rules, where if you get a exploration license, which is, after all, a state-sanctioned monopoly to explore a particular region and develop any of the resources you find within that, you have to explore it. You heard the minister of Ukraine talking about the dead licenses, right? Those are people sitting on things, not exploring. That's very bad if your goal is to increase exploration and development, right? So we want people that have the licenses to actually do something with them, and you have to prove that you're doing something with them, so you have to provide the data and a report of your work to the appropriate ministry. And then once the government possesses that data, it makes total sense for them to make it public on some reasonable time frame. The incentives for the private investors are all there, right? But now we don't have to, us as private investors, don't have to go reprove the same false positive 10 times, right? And by the way, data collected in one place is extremely valuable in other places. Think both in terms of training advanced ML and AI models, and think in terms of William Smith's old geologic map, right? It's obviously true that this gives you context for data over very long areas. Okay, so then data not paid for by private companies, but not put in the public domain, that's bad. We think that's bad. And unfortunately, it's the majority of jurisdictions around the world. Majority of jurisdictions around the world do not require reporting of the data, and the data does not become public at all. So we want that to change, and that's a free change that countries can make. And then finally, there's the category of paid for by the taxpayer and not in the public domain. That's egregious. And it exists. It's very common, actually, unfortunately so. Anyone here from the World Bank? Mark, World Bank? So the World Bank does a lot of good things. One of the things they do is fund geophysics and geologic surveys around the world, principally in developing countries, for all the reasons that I'm saying. And here's a quote from a World Bank official just before one of these surveys. They said, "The data obtained and promoted as a public good will reduce the costs and risks of private exploration and inform both public and private investment decision-making going forward." Hallelujah, right? Fantastic. That's cool. Okay, so here's the countries that the World Bank has funded programs in. The World Bank is funded by member nations, and member nations fund it through taxpayers. American taxpayers are the largest funder of the World Bank. Okay? Here's the availability of that data. So giant shout out to Nigeria and Malawi. They have made the data public. You can go to the website and you can download it. The other categories of the data are basically impossible to obtain. We've tried, and formally unavailable. This is bad, and shame on the World Bank. Because the World Bank should mandate, when they fund these things, that the data becomes public, and the World Bank should themselves make the data public. It should just be on a World Bank website. So we're operating on 4 continents right now, and we are trying to vote with our feet here. We're trying to be lead by example. So as some people know, we have an extremely large project in northern Zambia. It's got about 10 billion kilograms of copper, more than 4% grade. Super amazing project. We've flown geophysical survey in the region around it, extensive, and we just open sourced the data. We did it on our own. This is not required. It's been downloaded 435 times in the last 9 months. I expect that number to go up a lot today. It's there. Download it. It's for you. We've partnered with the Zambian government to digitize and make easily available a lot of their legacy data. There's incredible repositories of data they have in many of these countries. These are 4 KoBolders. I call them the public data avengers. And here they are working through the geologic survey, where you have over 100 years of data, working through all these maps. This is how the data was originally collected. And we're digitizing it. It is soon to be widely available. It's going to be available through a store, which is designed by us, and it'll be managed by the geologic survey department. Have something like 50,000 plus documents. There'll be a modest fee for the data. It's very cheap relative to collecting new data. Our preference is to make it actually free, but we're happy to partner with Zambia and have it be a small cost because the cost of the data will go to fund the GSD's budget, so that's cool. We want to do this everywhere in the world, and we are funding 100% of that project. Okay? Anyone know where this is? Belgium. This is Belgium. This is the Museum of Central Africa in Belgium. As probably everybody knows, Belgium had colonized what is now the Democratic Republic of Congo for over 80 years, and this museum's got lots of artifacts from that period, okay, including an incredible repository of geoscience data. We believe this data belongs to the people of the DRC. It is totally unavailable right now. You cannot even go and leaf through the paper. It is under lock and key. But it is a national treasure for the people of the DRC that will stimulate massive foreign direct investment. So it is our objective to digitize these entire archives and make them publicly available. I was in Kinshasa with my colleagues, Benjamin and Jen. You here? Benjamin, Jen. And just a few months ago, and this is a major part of our initiative there. We're going to be investing in DRC massively, and this is a key component. Everywhere we go, we like to digitize, explore, and develop, DED. Let's see, Ochudi, you're in the office, right? You're in the room, are you in there? Ochudi, there you are, Ochudi, welcome. In fact, everybody from DRC, stand up. This is incredible, actually. Stand up from the DRC. Yeah. Thank you. That is a long way to come. Welcome, thank you. We are so happy you're here. We have incredible partnership that we're forming with the Congolese government, with support from President Tshisekedi from the very top. This is a letter from the DRC's Geologic Survey to their counterparts in Belgium, saying this is a project that we want to get going and inviting us to go and asking the Belgians to provide access. And it's been tough going. The Belgians have been slow here. But I can confidently say we're making real progress. And so a couple of KoBold colleagues, along with a colleague from the DRC's Geologic Survey, were able to review the records very recently, and this is the start of this major digitization project, so this data can be put to great use for the benefit of all the people in the DRC. Thank you.
Yes, I know that museum very well. It's quite a history. If you go to Belgium, Brussels airport, it's actually just 15 minutes taxi from the airport, and highly recommended to see that history. Any questions for Kurt or comments about this making data public? I know that we have somebody from BHP here. That is, or you have a question? Yes, Brazil.
Thank you. I'm with Willow Consulting in Melbourne. What data we're gathering it and why we're gathering it? For example, we drill to look at grade and so on. We miss out on hardness, for example. In one drill core, you can achieve a lot of data, which will go into mining, stability of the pit, processing, cost of processing, and so on. And when we start looking at data integrally, what are we doing? Are we in the business of just getting rock and crushing it, or in the building of releasing wealth for the benefit of people? I call mining the process of converting natural capital into human capital. And that's how I see it. And it's for the benefit of people, ultimately, what it should be done.
Hear, hear.
Yeah, thank you very much, guys, for that wonderful presentation. So I think I really want to talk about the issue of data gathering. And Professor Jeff will agree with me that you can actually gather the wrong data. So I think one of the very important things we need to start talking about in Africa for the data availability is the procedure for data gathering. And apart from South Africa and maybe one or two other countries in Africa who has a standardized system of geological data gathering, most countries in Africa don't even have that procedure. So when people call me from Nigeria, for instance, and Ghana, say they want to do
It is definitely not just African countries. I would actually say there's not a single company in the world that has standardized how they organize geoscience data, and I would even include KoBold in that. We're trying hard, but it's an incredibly hard problem, and it is because the data is so indirect and such a mix of hard quantitative data that's telling you something very indirect, plus very soft qualitative data that is really a set of hypotheses wrapped together. The data is incredibly difficult to understand, right?
Yeah, and in addition to that, in the US, you talk about the SK1300. In Canada, you talk about the NI, 43101, the JOG. Now, sometimes people think Africa is just a country, and they don't realize that you have 54 countries who have like different geological survey and agencies. So how are we talking about developing a unified system to develop a standard for mining and mineral reporting, such as the SK1300 and the NI 43101? No investor is going to put in money in any of those mining projects without a standardized reporting technique. Most of the report that comes out from Nigeria they send to me, I just look at it and, of course, I have to trash them because there is no way I want to talk to an investor or a potential investor who is going to even put in money for that type of project. So we need to start devising a way to develop something like the SK1300 and the NI 43101, in the context of the African continent. And I think that is really going to help our data availability and reliability of the data. Thank you.
All right, thank you very much.